Unit 7 review time. So these are our standards that we've been looking at. Let's take a look at each one of them. Students know the definitions of solute, solvent, and solution. Well, that's not too bad. Solute is what you have less of. Solvent is what you have more of. It has more letters, see? And solution is a homogeneous mixture, which means it has one phase. Everything is evenly mixed. Okay? So if you add more solute, it gets more concentrated, more potent. If you take away the solvent, there's still more solute per solvent, so it gets more concentrated. Let's talk about 6b, and we can talk about concentration some more. How to describe the dissolving process at the molecular level by using the concept of random molecular motion. Okay, so what happens? Let's say we take, a solute here. Okay, this is my solute, and I just kind of drop it in to a bucket of water. Boop, boop, boop. Now, if this thing is soluble, what's going to happen is that the water is going to come and attract this and pull it apart. Okay, the water's pulling it apart. That's what it sounds like. Not really. And then the water's moving around randomly, right? So it's going to start moving these guys around randomly. So if I just move these randomly and then stop them at some point, well, that one somehow left the beaker. Okay, now they're more evenly mixed and it's more homogeneous. It's solution, right? So forces pull the solute apart, and it random molecular motion causes it to dissolve. Now, if we took this back, right, and we dissolved it, or we tried to dissolve it, but it's insoluble. Here, I'll change the color. This one's insoluble now. It's red. Bad. The water will try to pull it away, but the solute is too strongly attracted to itself, and so it just stinks to the bottom, and the water's like, well, forget you. Guess I'm not going to dissolve you then. All right, poor water. It's sad, and it cries because it's water. All right, so that's the dissolving process. Now, let's look at 6c, how temperature, pressure, and surface area affect the dissolving process. Now this one confuses people because there's two things that you got to think about. You got to think about solubility, which is how much can dissolve, and you got to think about rate of solution, which is how fast the solute can dissolve. Alright, so let's talk about one thing at a time. Let's talk about solubility first. So, new slide. Boom. Solubility. And let's talk for a gas, and let's talk for a solid. And this is, of course, assuming that it's soluble in the first place. So, how much will dissolve? Let's look at temperature and pressure. So, if you increase the temperature, for a gas, the gas particles start moving faster and the solubility will go down. So hot soda will contain less carbon dioxide. If you increase the pressure, the solubility will go up. Gas particles will be forced in. For a solid, if you increase the temperature, the solubility will almost always go up because it helps to break the solid apart and spread it through the solution. If you increase the pressure, the solubility will do nothing. It doesn't care. It is only impacted by temperature. Particle size, how fast you stir, all those things have no effect on solubility. So solubility, no effect. And what are those things that have no effect? Particle size, surface area, stirring, etc. Anything that's not pressure or temperature really has no effect on solubility. Let's go back up here. Boom, rate of solution. Let's talk about rate of solution. Okay, well, rate of solution, this applies across the board. Doesn't matter what phase it is. Rate of solution. And there's three main factors: temperature, surface area, or particle size, and stirring, or agitation. So if you increase the temperature, particles move faster, and the rate of solution goes up. If you increase the surface area, that means more solute is being shown, and the rate goes up. Now, a note about surface area. If you have a big block, this has less surface area than 4 small blocks, right? See, more of the side is being shown when you chop it up. So high surface area means low particle size. So if you want to think about it that way, you can. It's the same thing. Okay, if you stir something, it increases the contact and the rate goes up. So in your written explanations, always talk about the number of solute-solvent interactions. You can't see that. Let me help you. The number of solute-solvent interactions. Bam! Always talk about that. Be like, there's more interactions, so it dissolves faster. Or, and therefore there are less interactions, so it dissolves slower. And then I'll be like, I love you. Okay? That's what you need to do. 6D is talking about molarity. I know it says all this other stuff. I didn't teach you that, so I'm not going to test you. It's sad, isn't it, how little we learn in this class? If only we could learn more. If only. Molarity. Molarity is a unit, M, that's made from two other units, mole or liter. It's like mole and liter got, together. Mole got on top of liters. They had a baby and created molarity. How nice. It's a unit for concentration because it's a ratio of amount of solute, mole of solute, to liters volume of solution. So you have a high molarity. That doesn't mean you have a lot of stuff. It just means that in, your certain volume of solution, you've got a lot of stuff in there. Okay, but I could have a really big volume that's not as concentrated, but still has more actual stuff in it, right? But this is less concentrated than this, even though it has more little particles in it. So this has a lower molarity right here than this guy. Okay. Now how do we use this? We can use it as a conversion factor. So if I have a solution that's 3 molar and I have 2 liters of solution, how many moles do I have? Well, I just take 2 liters times, I know I want liters on the bottom, moles on the top. Well, this, right, the unit is moles over liters. So it's 3 moles over 1 liter. Liters cancels out. 2 times 3. Oh, my brain! 6 moles. Bam. Right? And so forth. You can do the same thing. If you're looking for molarity, all you need is moles and liters, and you just plug in your moles, and you plug in your liters, and then you do the math, and you find out your molarity. If you're looking for liters, you just take the molarity and you flip it. Flip. Bam. Wow, so much learning occurred on this page. Let's go back to our standards. Molarity. Okay. Acids and bases. Alright, let's go over definitions. Acids give H+. So for example, HCl, when you put it in water, boom, it produces a hydronium ion because the H+ goes to the H2O, and then it has this Cl- left over. So acids give H+. Bases take H+. So NaOH plus H2O, boom. This, that's a bad example. Okay, well, whatever. This H goes over here and makes H2O. I know, crazy. That's why it's a bad example, because it's making the same thing. and then boom, you have the OH minus left over. So if you produce hydroxide ions, it's almost always a base. So take H plus or produce OH minus. Oh my gosh, this video has been 10 minutes. It's so long. Hold on. We have an exam, a celebration of knowledge. Hold on. Okay, properties of acids and bases. Let's see. Let's just list as many as you can. Okay, do it with me. That's right. They're sour. They give H plus. They turn litmus red. They dissolve acid or dissolve metals and produce hydrogen gas. What else? They corrosive. I don't know. Look up the rest. I think that's pretty good. Whoa, what happened? It disappeared. Man. Okay, well, we'll just do bases. You can go back and pause if you need to. Okay, so bases. They're bitter. They take H plus. They're also corrosive. Oh my gosh, so much corroding. They... What else? Turn litmus blue. Slippery. I feel like I'm forgetting some, but whatever. That'll be good. Oh, hey. No, I thought it was our acids. I don't know what's happening right now. My program's tripping out. Too much acid, I guess. Okay, strong acids and bases fully dissociate, and weak acid bases partially dissociate. Well, it's right there in the standard. I don't feel like I have to review that for you. And both can be characterized with the pH scale. pH scale. It's called pH because power of H, but I don't teach you how to calculate it, which is really sad. You should look it up and become smart. Goes from 0 to 14. This side is acid. This side is base. 7 is neutral. If it's all the way over here, that's a strong acid. If it's somewhere in this little neighborhood, 4 to 6, that's weak. Base 6, same thing. Closer it is to neutral, it's a weak base. Stronger it is or farther it is to 14, closer it is to 14, the stronger it is. Okay? Review your notes, do your homework, come in ready to rock. I'm ready to rock. Okay, bye-bye.